So this is continuing the series about counting, and at this point we've learned about 4 kinds of counting formulas for words, permutations, combinations, and multisets. We have not learned any of the formulas for these yet, just the symbols. So nCr is the number of combinations of size r that you could draw from a set of size n. We learned that the combinations are just subsets. Order does not matter. Repetition is not allowed. And nPr is the number of permutations of size r that you could draw from a set of size n. Like the combinations, no repetition. You can't have one element belonging to it twice, but order matters. The permutation ABC is different from ACB. Now, we don't have formulas for either one of those yet, but what I want to do in this video is to see how those two formulas are related, an equation connecting the two of them. So then if I work out one of them, I'll get the other one for free using this formula. And this will help you to better distinguish between permutations and combinations when you see the difference. So I'm going to compare nPr and nCr with small numbers for the n and r. So I'm going to compare 4p3 with 4c3, where the lists are small enough that I can write them down. So here's a set of size 4. Its members are A, B, C, and D. I can easily list all the subsets or combinations of size 3. If I'm going to pick 3 of these 4, I just have to decide which one to leave out, you know? So I've got the one where I left out the D, and the one where I left out the C, the one where I left out the B, and the one where I left out the A. So I have 4 different combinations of 3 elements. Okay, so 4C3 equals 4. There they are. I just listed them and counted them. We'll get a formula in another video later. Okay. But 4P3 is bigger. Why? Because any one combination is going to break up into 6 different combinations. Each one of my 4 combinations breaks up 6 different ways if the order matters. So, I've got 2 different orders that I could put it in if I decide to start with the B. But then if I decide to start with the C, if I start with the C, there's 2 different orders I could put it in, and if I start with the D, there's 2 different orders I could put it in, starting with the D. So each one combination corresponds to 6 permutations. Okay, so for P3, is 6 times for C3. There were 4 combinations, but 24 permutations. So the number of permutations is going to be some number times the number of combinations. So I just drew a box there to fill in. It's the number of ways. The 6 was the number of ways that you could arrange these 3 letters, the number of different orders that you could put the 3 letters in. Well, sorry for the hyphenization there, but the number of arrangements. Okay. So how did I get that 6? There were 6 ways to arrange 3 objects. Why? Well, in a previous lecture, we did that with the 5 pins. Previous lecture, we did how many ways can I arrange 5 pins? 5 choices for who goes first, and then 4 choices for who goes second. So by the time you got your first 2 pins, there were already 5 times 4, 20 ways you could have done it. 5 times 4 times 3 times 2 times 1. For the total arrangement of all 5 pins. How many ways can you arrange our objects? R factorial. So nPr is R factorial times nCr. Now the way I'm going to use that in a later lecture, turns out nPr is easy to figure out. And nCr would be complicated, except now we know you get whatever you have for nPr, you just divide it. Divide both sides by R factorial. Divide both sides, cancel out, waka waka. So what I get is nCr equals nPr times 1 over R factorial. divided by r factorial. Okay. So in another video, we'll figure out nPr, and then we multiply by 1 over r factorial, and that gives us nCr as well. So we'll get both formulas in one calculation. So the takeaway from this video, thing you want to memorize, that thing in the box there in the corner. nCr is nPr times 1 over r factorial. That's all for this video.